issue. Hello, how are you doing? I didn't hear any of that. Oh, yeah. Paradise is a nice place. Whoops. All right, so let's see, things to remind you about is assignment number 5 next week. And well, I'll probably stop saying it, but I'll keep writing it in the slides. But formal report is the second last day of classes, I believe. Okay, so we've spent a lot of time over the last week or so trying to work with data that follows a straight line and then finding the best slope and intercept for the line that goes through those data and their uncertainties. We use the method of the maximum likelihood, where we started with a Gaussian distribution. We calculated the probability of a particular data set arising, and then we adjusted the slope and intercept until we maximized that probability. So that was the method of maximum likelihood. Last class, we spent a bunch of time looking at different ways that we could linearize data so that we could then apply these least squared weighted fits to find the slope and intercept. We ended by saying sometimes it's just not possible to analyze data using a straight line. And so when that's the case, we have to come up with new methods. And so we're going to start developing one of those new methods today. Okay, so let's just start with a simple example. And this is an example that you would have come across if you did, say, the black body radiation experiment. So in that experiment, you had to measure the temperature of a furnace using a thermocouple. The thermocouple outputs a voltage, and from that voltage, you can then calculate the temperature. The way you did it is you looked up some calibration tables, and if you plot the calibration, so you plot temperature as a function of the voltage you measure over a small range of temperatures, it is pretty linear. But as you go over a larger and larger and larger range of temperatures, you actually start to see some deviations, and it starts to look like something with some curvature, and then you have to fit that to a polynomial. So for example, the calibration of a thermocouple over a large span of temperatures is non-linear, and you ended up fitting T versus V to a polynomial. Okay, and so what we might say is t is equal to a0 plus a1x plus a2x squared. Maybe it's a second order polynomial is sufficient. And there's just no way to linearize that, right? We could, we kind of had this example last time. If the a0 wasn't there, we could divide by x. I guess I should say, if we're talking about a thermocouple calibration, this would be voltage. So if the a0 wasn't there, we could divide by v, and then t over v would be linear in voltage. But once this a0 is there, that stops us from making that kind of change. We're just stuck. This is not a linear function. We can't analyze this with a straight line. So this is not linearizable, if that's a word. I guess it probably is. Okay. All right. So what we're going to want to do is we want to fit data to, just to be in general, instead of specifying a temperature, this will be just something like y. It could be temperature if we're talking about a thermocouple is equal to a0 plus a1x plus a2x squared plus, and we don't have to stop at quadratic. We could just keep going up to, and let's say a m to the x m. Okay. So we're going to develop a method that would allow us to do this kind of thing. The result is, again, going to be something where we'll exactly be able to find the values of these m coefficients based on the data that we measure. But in fact, we can actually generalize this a little bit more. Okay. So in fact, the technique that will develop can be further generalized. Okay, so we're going to want to fit data to a function of the form. Okay, so it's going to look like this. We'll have a y of x is equal to, I'm going to write it like this. I'll have a1 and then some function of x1 plus a2 times some function f2 of x, and we'll keep going up to am some function of mx. Okay, so it's just like this, except I've dropped the a0 term, and like we could have a coefficient without any function of x, like this f1 of x could just be set to be equal to 1, and then that would recover just having this term not multiplied by x. Okay, so the only restriction is that when we do our analysis, we're assuming that the unknown parameters that we're trying to find are the coefficients and only the coefficients. So in other words, we're assuming that anything in these functions doesn't involve unknown parameters that we're trying to find. Okay, so that's the only restriction. So where the fk of x are functions of x that do not involve the unknown parameters a1, a2 up to am that we're trying to find. Okay. So for example, whoops. For a polynomial, we could set f1 is equal to 1, f2 is equal to x, f3 is equal to x squared. And if it was just a second order polynomial, then we could say all the higher order, like f4, f5, and so on, are just 0. And so that would be our second order polynomial. Okay. Well, fortunately, a lot of what we have to do to develop this method is actually follows exactly what we've already done for the linear fits. In fact, what we could say is what we're really doing is we're generalizing what we did for linear fits, and then the linear fit is just going to be the special case of what we're going to do now. And that special case is f1 is equal to 1, f2 is equal to x, and all other f's are 0. That would just be our straight line fit. Okay, so what we'll do is we'll use the same method of maximum likelihood, that was developed for linear fits. And what I hope that we'll find is that we'll end up doing a lot of the same things. Like for linear fits, we ended up writing a matrix equation, and then we inverted the matrix to find our best fit parameters. We're going to do all of that stuff again. It's just the math is going to be more messy, that's all. Okay, but the technique is the same. So if you look back to what we did, we minimized this thing that we called chi-squared. Okay, and remember that chi-squared was we sum over all of our n measurements of, well, let's see, it was 1 over the uncertainty times yi minus y of xi. And then we had to square all of that. And so let me just remind you, we measure xi and yi plus or minus sigma I for I equals 1 to n. Okay, so that's all the data we collect. So everything in here, this sigma I, the yi, and the xi are all known. And then the y of xi is going to be, well, in this case, it would be a1, f1 of xi plus a2, f2 of xi plus and so on up to m. So however many parameters we have that we're looking for, and we could denote all of that as the sum of, let's do j equals 1 to m of aj fj of xi. Okay, in fact, when I'm looking at my notes, I have used a k here. So I'm going to be just consistent with my notes because I am not smart enough to make that conversion in my head. So this is going to be ak fk of xi. All right. So all I'm going to do is I'm going to put this y of xi into here, and I'm going to write it in this form. Okay. All right. So what we're going to do is we're going to minimize this chi-squared is equal to the sum I equals 1 to n of 1 over sigma I, yi minus the sum of k equals 1 to m, ak, fk of xi, and then we have to square all of that. And we have to minimize with respect to all of the unknown parameters. So it's a1, a2, a3, up to am. And so if you think back to our linear fits, we had only two parameters. We had the slope and the intercept. And so we had to minimize this chi-squared with respect to each of those. That led to a system of two equations and two unknowns. And we ended up writing that as a matrix equation. The matrix was an 2x2 matrix with some column matrices on the other sides. What we're going to end up with here is m equations, because we're going to have to do m different derivatives of chi-squared, all equal to 0. We're going to write that as a matrix equation. The main square matrix will be m by m. Okay, so it's going to be kind of a big thing, but that's okay. We'll grind through it. Okay, so this involves partial derivatives of chi-squared with respect to the parameters, let's say al. Okay, I'm not going to use k here because we're going to take these, like k could be 1, 2, 3, 4, 5, 6, 7 up to m, and then this L is going to be just selecting one of those. All right, so what we'll end up with a system of m equations and m unknowns. All right, so let's get to it. So we're going to take the partial derivative of chi-squared with respect to al. All right, and we'll try to do this slowly. Let me know if there's any step that needs clarification. All right, so chi-squared is just all of this big mess. So I equals 1 to n of 1 over sigma I. Yeah, that's right, 1 over sigma I. And then we have yi minus the sum of k equals 1 to m ak fk xi. And okay, so this derivative can move inside sums as long as the subscript here is not the same indice of the sum. And moreover, this yi doesn't involve any of the a parameters. So when we take the derivative, that will go away, and this will end up coming in. The first thing we have to do is recognize that all of this stuff is squared. So we have to do chain rule. When we do chain rule, the first thing that happens is the 2 comes out in front, and then we have to take the derivative of everything inside the square brackets. Okay, so we'll try to write this out in some detail. So first, let's deal with that chain rule part. We get the 2 coming down from the square, and then we have the sum of I equals 1 to n, and then there's going to be a bunch of stuff. So we're going to get the 1 over sigma I. We're just rewriting everything in the square brackets again. K equals 1 to m, ak fk of xi, and then curly bracket, square bracket, and then this is all going to be times. So here's the chain rule part. Now we take the derivative of everything that was in the square brackets without the square. So it's d by dAl, and it's 1 over sigma I yi minus the sum of k equals 1 to m ak fk of xi. And so there's no square, and then I'm just going to close this bracket. Okay, so this is the part here. The derivative of the yi is just going to be 0 because it doesn't involve an a at all. All right. So let's just consider this d by dAl of 1 over sigma I yi minus the sum. And we'll just do it bit by bit. So this is going to be equal to minus 1 over sigma I d by dAl of k equals 1 to m ak fk of xi. All right, so this is, this is independent of the a parameters. All right, now this thing will come inside the sum. So this is going to be minus 1 over sigma I, the sum of k equals 1 to m, dak dal fk of xi. What is this derivative? That's right. It's delta KL, exactly. And so this is minus 1 over sigma I, sum of k equals 1 to m, delta KL, fk of xi. And what does this become? It kills the sum. So yeah, there's no sum. So we're going to get a f of L, exactly. This is going to be f of L xi. And so this whole derivative boils down to minus 1 over sigma I FL of xi. All right, so this thing, let's call this just for now, call that star. So what we've done is we've worked out this, and we got minus 1 over sigma I FL of xi, and this is from star. Okay, so this sigma I is going to combine with this sigma I, so we'll get a 1 over sigma squared. The minus sign we can stick out front, and then we just have this FL, which will multiply all of this stuff. And so let's see, what does that look like? So therefore, this derivative that we're doing, this chi-squared derivative with respect to AL is going to be minus 2 sum of I equals 1 to n of, so in fact, what I'm going to do is I'll write the FL here, FL xi over the sigma I squared. Okay, so all I've done is put this sigma here, combined it with this, and put this FL over here. That's fine. It can move through all of this stuff. This is a sum over I, and the sum over I is out front. So as long as we don't move it outside the sum over I, we can kind of move it around a little bit. Okay. And then we just have to write all of the other stuff that was there. So it's a yi minus the sum of k equals 1 to m ak of fk times fk of xi. And so there it is. That's the derivative. And if we're doing a minimization, it has to be equal to 0. All right. I don't care about the -2. We can just divide by -2, and then we just have this big sum of all of the stuff is equal to 0. You can see that we have one term that's going to be positive, and then one term that's going to be negative. And so what I'm going to do is I'm going to take the negative term and move it over to the other side. And so let's see, what would we be left with? Therefore, the sum from I equals 1 to n of, how do I want to write it? I will write it yi fl xi over sigma I squared is equal to. So we've dealt with this times this, and that's staying on the left. We're going to move this one to the right, and we're going to have to multiply it by this stuff. And the sum over I is going to have to come with us. So it will be the sum of I equals 1 to n. Let's see, FL over xi, FL of xi over sigma I squared. And then we have times the sum of k equals 1 to m ak fk of xi. So this is one of our important results. And I'm going to claim that this represents a system of m equations and m unknowns. The reason that it's m different equations is because we can put in here m different values for L. L could be 1, 2, 3, 4 up to m. And we'll write out an example just to see how this works. So this result represents a system of m equations and m unknowns. The unknowns, we already kind of can list them. That's just A1, A2, up to AM. And the reason it's m equations is because L could be equal to 1, 2, 3, up to m. So let's do an example. Let's suppose that y is just our second order polynomial. So this is kind of the simplest example we could write down that goes beyond just a linear fit, okay? So in this case, we would say that our f1 is whatever multiplies the a1 coefficient, and that's just a 1. So f1 is just equal to 1. F2 is whatever multiplies the a2 coefficient, and so that's just x. And F3 is going to be the x squared. All right, so I'll keep this up here so we could try to write down this. So in this example, we're going to expect to write down a system of 3 equations. Okay, so let's just try L equals 1, F1 equals 1. All right, on the left-hand side, we have the sum of yi times FL divided by sigma I. FL for L equals 1 is just going to be a 1. Okay, so we're going to have the sum of I equals 1 to n of yi over sigma I squared is equal to. Now we have to do the right-hand side. Again, the FL is just going to be a 1. And so we're going to get the sum of I equals 1 to n. FL over sigma I squared is just going to be 1 over sigma I squared. And we could write out this last sum too, because we just had n equals 3. So it's just 3 terms. It's A1, F1 plus A2, F2 plus A3, F3. And so, yeah, it is, but it is the y, but then we just have to put the I subscripts on x. That's right. Yep, but that's exactly what it is. It's just going to be A1 plus A2 xi plus A3 xi squared. So that's one of our equations, and then we just do the L equals 2 equation with F2 is equal to X. Okay. So let's see. We'll keep that up there. So it's going to be exactly the same, just wherever we see an FL, instead of a 1, we have to put an X. So there'll be an XI here, and there'll be an XI here. Okay, so it's going to be the sum of I equals 1 to n of yi xi over sigma I squared is equal to the sum of I equals 1 to n xi over sigma I squared, and then that second sum is exactly the same, it doesn't change. And you could probably already see what the third equation is going to be. The third equation is going to involve f3, and it's going to be x squared. So we'll have an x squared here and an x squared here. Everything else is exactly the same. No, you have to be careful with that. Like, you can't just, like, I can't divide this by this and then just cancel everything except the xi, because it's inside of sum, that's why, yeah. These are, just think of these as numbers, like you've made these measurements, and so you have the product of x and y, but then you have to sum them up for all of the values of n. And so it's just dividing these two is not going to be the sum of xi. Yeah. So let's do L equals 3, F3 is equal to x squared, and it's going to look exactly the same, except we get an x squared here. And an x squared here. Whoops. Here's xi plus a3xi squared. All right, and so this is our system of 3 equations for our example of fitting to a quadratic. All right, what I'm going to do is I'm going to go back here. We have already used star, so I'm going to label this with a number sign. And I'm going to claim that we can represent this equation as a matrix. And so we're going to try to do that. So we can represent the number sign equation as a matrix equation. And so we're going to write it this way. Beta is going to be alpha times A. And so in my notation, matrices with just one thing, one underline, is going to be a column matrix. And this one with 2 underlines is going to be a square matrix. So this is a column matrix. Its dimensions are going to be m by 1. And this is going to be a square matrix. And it's going to be an m by n matrix. And then this is another column. Okay, so let's go back to number sign. The column matrix is pretty easy to identify. Its entries are just going to be like this. The first entry is going to be the L equals 1 entry. And then the second one will be L equals 2, 3, 4, 5, up to m. Okay, so that beta column matrix is just the left-hand side of equation number sign. So beta, I'll do it like this. Beta L is just going to be YIFL xi. Okay. Now, the A matrix is just going to be A. So the first entry will be A1, then A2, A3, down to AM. And so that means what we're left with is alpha, and I'll give it subscripts LK, and it's going to involve FL and FK, so that's why we had those indices L and K, and it'll have a 1 over sigma I squared in it. Okay, so we'll just write it down, and then we'll confirm that it works. So this is sum equals I equals 1 to n, 1 over sigma I squared, and then we said it's going to have an FL, and it's going to have an FK. Okay, and let's just note that alpha is symmetric. So that means alpha LK is equal to alpha KL. And you could see that because if I just switch indices here, nothing changes. It's still an F times an F, or if I switch the orders. So that's the symmetric nature of this square matrix. All right. Let's do an example to confirm that this works. So let's see. Ooh, I don't want to cross a page. All right. Example. Let's take y equals a1 plus a2 x plus a3 x squared. So we already know that f1 is 1, f2 is x, and f3 is x squared. So what we're going to do is we're going to write down the elements of our matrices using these definitions. Then we're going to do the matrix multiplication, and we're going to confirm that we get this system of 3 equations back exactly. Okay. So let's see. We'll start with the beta matrix. So it's going to be sigma squared yi times FL. So we're going to have, they'll all have the sum of I equals 1 to n. They'll all have the 1 over sigma I squared. They'll all have a yi. The only thing that's different about these entries is the value of FL. So in the first case, it is FL is L equals 1. And so F1 is 1. So that first entry is complete. The second one is L equals 2, where F2 is equal to X. So we get an XI here. And then the third one is F3, and we get an XI squared. So that's our beta matrix. All right. And then it's going to be equal to some big square matrix. And then we're going to have our A matrix. And this one is pretty easy. We have A1, A2, A3. And so this is our A column matrix. All right, so now we have to fill in the alpha thing. And it's actually not that hard. They're all going to involve the sum of I equals 1 to n of 1 over sigma I squared. And so we can put all of that stuff in. 1 over sigma I squared. And so I equals 1 to n sigma I squared. We've got to write it 9 times. Okay. Yeah, I could. It is. People get so impatient when they have to do 3 minutes of tedious work, but they should just suck it up and do it. Okay, good. So now what we have to fill in are the products of FL and FK. All right. So the 1, 1 entry is just going to be F1 times F1. But F1 is just 1. So I've already got that one with a 1 in there. So that one's done. And then we have a 1, 2. And so that's going to be F1 times F2, which is 1 times X. So we're going to get an Xi here. And we already know that the alpha matrix is symmetric. So this one is going to be the same. And then we have like a 1, 2 entry. So that's F1 times F2. Sorry, this is 1, 3, sorry. So this is F1 times F3, which is 1 times X squared. And so we get a Xi squared here. And then it's symmetric, so this one's Xi squared. Here's the 2, 2. So it's F2 times F2. It's X times X. We could do this one 3, 3. It's F3 times F3, X squared times X squared. This is Xi to the 4th. And then we have like a 3, 2 or a 2, 3. So that's X times X squared. So we get Xi cubed and Xi cubed. All right. So let's do matrix multiplication. In fact, I'm only going to do one of the multiplications. You could do the others if you wanted to confirm this. Let's check the first equation. Okay, so we take the first, I guess we should just label this as alpha. We'll take the first element of the beta column matrix. So this is going to be yi over sigma I squared equals. Okay, so we have to do that top row multiplied by this A column matrix. And so it's going to be at A1. And then the 1, 1 element is just 1 over sigma I squared. Then we get plus A2. And then we have an xi over sigma I squared. Plus A3. And that's a xi squared over sigma I squared. And so what I want to do is I want to compare this to the first equation that we had. We could simplify this a little bit because they all involve the same sum. So instead of writing a sum of 3 sums, we could write a sum of 3 terms. And so this would be pi equals 1 to n of, let's see, they also all have a 1 over sigma I squared. And so then we just get a A1 plus A2 xi plus A3 xi squared. And if we go back and look at our 3 equations, yi over sigma I squared is 1 over sigma I squared, A1, A2, xi, A3 xi squared, exactly the same. You probably noticed that some of the terms in the alpha matrix had like an x cubed and an x to the 4th, and we don't have those things written explicitly here, but I could distribute this and I would get an xi cubed here. I could distribute this and I would get an xi to the 4th here. So if you do the other 2 equations, you will get these 2 exactly back. So this matrix equation, beta equals alpha A, is just a compact way of writing that big mess that we got from the minimization of chi squared. Okay, so this is the L equals 1 equation that we previously wrote down. All right, good. So back
to beta is equal to alpha times A. So what we're trying to do is we're trying to solve for A. And if you think back to what we did for the linear fit, all we did is we multiplied both sides of this by the inverse of the square matrix. We called it capital A when we were doing the linear fits, but this is kind of the new version of that capital A matrix. All we're going to do is invert alpha, and we'll isolate A, which is our unknown parameters. And so we want to solve for the unknown parameters at AK. So therefore, we could write that alpha inverse times beta is equal to alpha inverse times alpha times A. But this thing is just the identity matrix. So whoops, that's not how you spell identity. This is the identity matrix. And so therefore, well, so this is I times A, but a column matrix times the identity matrix is just what? It's just the column matrix back again, right? And so therefore, A is equal to alpha inverse times beta. And if you go and look back at the definitions of beta and alpha, where are they? Here they are. Beta involves sigma, yi, and some known function of xi. We know all of the xi, we know all of the yi, and we know all of the sigma values. And so we could calculate every single element of beta. Likewise, alpha involves known functions of xi values that we've measured, and we know the uncertainties, and so we could calculate everything about alpha and then find its inverse, and that just leads to A. So we know everything to calculate alpha and beta. Therefore, we can find A, which is a column of all of our unknown parameters. Now, admittedly, inverting a large square matrix is not straightforward. If it's a 2 by 2 matrix, we can do that. But this is in general an M by M matrix, which could be very large. And we don't want to do that by hand, but you can do it in software, whatever you like to use, MATLAB, Python, Maple, whatever tool you have. So in general, it is not easy to manually invert a large M by M matrix, but it can be done easily in software. Okay, we have just 2 minutes left. So all I'm going to say is that usually the inverse of alpha is denoted as epsilon. And the reason they do that is because they're going to call it the error matrix. And I guess epsilon is supposed to look a bit like E, which is kind of standing for error. So usually alpha inverse is defined to be epsilon, which is called the error matrix or the covariance matrix. What we're going to find is, just like we found for the linear fits, is that the diagonals of the error matrix give the uncertainties in the best fit parameters. So if we want to know the uncertainty in A1, it's going to be the 1, 1 element of the error matrix or the covariance matrix. It's so the 1, 1 element would get the square of the uncertainty in A1. The 2, 2 element of the error matrix will give the square of the uncertainty in A2 and so on. So it'll be a bit of work, but we will show that the diagonal elements of the epsilon matrix give the square of the uncertainties and the best fit parameters AK. So specifically, epsilon KK is going to be equal to sigma K squared. And so that's what we'll try to do. Well, sorry, this is a stupid notation. I don't need to, I'm selecting a specific element of the square matrix, so I don't need underlines here. Okay, good. So that's what we'll try to do next time. I guess that'll be Wednesday of next week. So have a good weekend, everyone, and we'll see you then. I guess I'll see some of you on Tuesday.